me some example. The borosilicate glass or BK7 glass. This is a very popular medium used in fabricating optics like lens or mirrors or wet plates and so on. Here we assume the input pulse duration is 10 femtosecond. And if the input pulse is transform limited Gaussian pulse, you can quickly calculate the corresponding bandwidth, right? Because the time bandwidth product is a constant 0.441. So if you substitute 10 femtosecond in the denominator, you got 44 terahertz. Okay, 10 femtosecond pulse, 44 terahertz bandwidth in theory. And if we assume this laser pulse is centered at 800 nanometers, say from a sulfide laser, and then we send the pulse passes through a BK7 glass, and you can calculate the beta 2 curve, the GBD parameter, as a function of wavelengths. Here I assume the wavelengths changes from 600 nanometers to 1700 nanometers. This happens to be the range of typical optical spectrum analyzer, OSA. 你的光谱分析很常见，可以看到的范围就是600到1700奈，我就拿这个范围来做计算。那计算的方法是什么？就是上一页的公式来。I use this formula. Okay. I need to find the Selma equation for BK7 glass. Okay. I can numerically calculate the second order derivative of index. Then using equation 1, I can calculate beta 2 as a function of wavelengths. Okay. So this is the result. And since the working wavelength is centered at 800 nanometers, so look at 800 nanometers, you can find the corresponding beta 2 is 44.6 in units of femtosecond squared per millimeter. Okay. Then if we assume the thickness of the BK7 glass is 1 centimeter, okay, then you can use the formula in the previous page. The output pulse width is about beta 2 times L times bandwidth in terms of angular frequency. So this is 2 pi constant times bandwidth in terms of non-angular frequency, delta nu, 44 terahertz. Okay, so beta 2 is here, big L is 1 centimeter, delta nu is 44 terahertz. So multiply them together, you got 124 femtosecond. So 10 femtosecond in, 124 femtosecond out, stretched by a factor of more than 12. So you can easily sense how serious the dispersion could be. Right? Just 1 centimeter thick glass, okay, it's transparent, no absorption. And the induced dispersion is so huge, you can stretch your input pulse by 12 times. Okay. Let me ask you, what happens if the thickness is reduced to just 1 millimeter? What is the output pulse width? So I heard 12.4 femtosecond. Okay. If I further reduce the thickness to 0.1 millimeter, what is the output pulse width?
You might not be able to calculate from this graph.
Correct. If you still use this formula, you will get 1.24 femtosecond. It's post-compression. 10 femtosecond in, 1.2 femtosecond out. Wow, what a wonderful work. Without doing anything, just use 0.1 millimeter thick glass. You got a post-compression of a factor maybe 7 or 8. It's impossible. In that case, this formula is no longer useful. Why?
Because your the bandwidth can be broken.
The bandwidth is broadened. In the case of dispersion, the power spectrum remains. No change about your power spectrum. You will have no new frequency components. You will also sacrifice no frequency components. Okay. Everything is the same in terms of power spectrum. So why this formula does not work if the thickness L is too short?
因为它直接把 delta T in 直接忽略掉，就是它只算那个做不出来124，所以就是你应该要先把 delta T in 考虑进去，所以1公分会增加114个 femtosecond 这样子算，应该会比较准。
Great, you have deep understanding about the derivation of this formula. Although this picture is quite easy, but be careful. It only applies when your output pulse is much broader than your input pulse. This picture works. Otherwise, it's a matter of redistribution of your different frequency components within your envelope, input pulse envelope. The output pulse duration will not be, can never be shorter than the input. Right? If your input pulse is already transform limited, there is no way you can even compress it without creating new frequency components. Okay, so be careful. This picture only applies when the expected pulse duration is already significantly broader than the input pulse was. So in our example, this is okay. Input just 10, output 124. So the formula it should be accurate. But if it's only 12.4, it's controversial. On the verge of value. If it is 1.24, no way. It's impossible. Good. Then, material dispersion properties. We might have discussed this before. By the model of harmonic oscillator, you can derive your absorption spectrum should be like the blue dashed curve. Your index spectrum should be like the red solid curve. Okay. So you can see around the absorption peak, your index of refraction actually decreases with frequency. But on the spectral wings, your index of refraction increases with frequency. Okay, so this is the typical phenomenon you can observe. Then, if we draw the index of refraction against not angular frequency but wavelengths, what do you have? You should get something mirroring of the red curve, right? Because higher frequency means shorter wavelengths. So you should get something like this. For each absorption, like UV absorption, you get a characteristic curve, like the mirroring of this one. For another absorption, like infrared absorption, you got another characteristic curve, and they can be concatenated with each other. So you got the index of refraction spectrum. And I use two background colors to identify two different regions. Say, around the gray shaded area, this area you have a positive slope, right? And it's it refers to anomalous dispersion, just like here. Around the absorption peak, your index of refraction appears anomalously or unusually, because typically you are working with transparent regions. So here you got a very different characteristics. Anomalous dispersion, characterized by positive slope of index of refraction spectrum. Conversely, in the yellow tone region, if you have negative slope, you can see the index decreases with wavelengths. This is the normal dispersion area. Okay. If you use the slope of index as the definition of anomalous or normal dispersion, this is the way we can categorize it. Okay. The gray area, anomalous dispersion; yellow area, normal dispersion. And this is used in classical optics. Because like this picture, this is a prism, right? If you shine a white light, like sunlight, through the prism, you got a rainbow outside, right? And the order of colors of this rainbow depends on the dispersion sign of this prism. Usually this is normal dispersion, so you will have red color first and blue color last. If you got the reverse, it means you are using a material of anomalous dispersion. And then this is a very historical phenomenon. So classical optics uses this definition. The sign of first order derivative to define normal or anomalous dispersion. But the same curve can be divided differently if we use a different definition. Okay? For example, here, gray area, the second order derivative is negative. So it means a convex function. This is still around the absorption peak, so this is anomalous dispersion still. But you can see, in addition to the area around the absorption peak, there is another region with negative curvature, okay, or a convex function. So both the gray area and the cyan area represent anomalous dispersion if you use second order derivative as the definition of normal or anomalous dispersion. Okay? And similarly, the yellow area, you have positive curvature or a concave function. They represent normal dispersion. Okay. And this definition is used in the community of ultrafast optics. The reason is it is the second order derivative instead of first order derivative, defining the sign of chirp, up chirp or down chirp. It depends on second order derivative, just as what we just derived, right? The beta 2 coefficient is proportional to n double prime instead of n prime. So it's up chirp or down chirp depends on second order derivative or curvature of the index curve. So different definitions, different results. Okay, any questions? 传统光学的人，他没有超短脉冲嘛，没有 chirp 这件事，他关心的是什么？3棱镜出来颜色的顺序。那这件事用一阶微分定义，所以用一阶微分定义之下，你就会得到一个结果。只有在 absorption peak 附近是 anomalous dispersion， 一离开就是 normal dispersion， 很单纯。但是在 ultrafast optics 里面呢 ，chirp 是 up chirp 还是 down chirp 是我们关心的事情，而这个必须用2阶微分而不是1阶微分决定。你用2阶微分来当定，你就会发现 anomalous 不只出现在 absorption peak 附近， 在远离 peak 的中间也会有一个区域是 anomalous， 虽然它的折射率递减，按照第一种定义它是 normal dispersion， 但是按照第二种定义，因为凹口向下，它变成 anomalous dispersion， 这里可以产生 downward pulse， 这里可以产生 downward pulse， 这里是upward pulse。 Okay, another example. Transmission and dispersion of BK7 glass. So this is the absorption spectrum, transmission spectrum I retrieved from the website of Solabs, a company selling optics. Okay? So you can see for a piece of BK7 glass of 10 mm thickness, the transmission spectrum is pretty flat and high over this region. Okay. So you can see clear UV absorption here, about 320 nanometers. Okay. Another infrared absorption here around maybe 2800 nanometers. Within the between them, you've got flat, transparent region. 就代表这个 glass 可以用在几乎整个可见光都可以用，近红外光也可以，一直到 maybe 2.7、2.8的 nanometer， 你进入 mid infrared， 它开始会吸收，不能用，这整个 region 是可以用。但有些人他必须操作在紫外光 ultraviolet。 那么 BK7 maybe 就有点风险，因为它到300多纳米它就会吸收，所以有一种叫做 UV grade silica， 还是 silica base， 但是有经过一些特别的处理 ，UV absorption can be down to 170 nanometers, so it's pretty flexible. If you want to access UV optics, you might need UV grade silica instead of BK7. This is no longer a good choice. And I also conducted the numerical simulation for index of refraction as a function of wavelengths. Again, from 600 nanometers to 1700 nanometers. You can see this curve, the red curve, a monotonically decreasing function of wavelengths. Okay, so in terms of classical optics, this is normal dispersion, right? Within the entire region, spectral region, this is normal dispersion. But I also calculated beta 2 as a function of wavelengths. I got positive beta 2, 0 beta 2, then negative beta 2. So if you check the 0 beta 2, it's 1322 nanometers. That means when wavelength is longer than 1322 nanometers, you got negative beta 2 or anomalous dispersion in terms of ultrafast optics definition. But in terms of classical optics definition, it is still normal dispersion. Okay. Then, second order dispersion or third order phase. Before we look at the formulas, do you still remember the impact of third order spectral phase? It's very different from the impact of second order spectral phase. Basically, second order spectral phase only broaden your pulse. And maybe it does not change your pulse shape too much. A Gaussian input, maybe still a Gaussian output, but only broader. But if you introduce third order spectral phase, cubic phase, what will happen? It's no longer just pulse width broadening. It's a matter of shape distortion, right? It becomes asymmetric function, and maybe you will have oscillating tail, right? So in what occasions third order spectral phase matters? Okay. Two cases. First, the working bandwidth is very large, such that this number is bigger than this number. The meaning of the first number is the phase accumulation, the cubic phase accumulation, right? Beta she times omega cubic, but omega is a variable. You need to substitute some number for that variable. And the reasonable number is the bandwidth, right? So if you substitute delta big omega bandwidth into the variable omega, this is the total phase due to the cubic term. And this is the total phase due to the quadratic term. If this term is bigger than this term, of course, cubic phase matters. It's more important than the quadratic phase. A second case, if your spectral center is close to the zero dispersion wavelengths. What is zero dispersion wavelengths? It's the wavelength, a very special wavelength, where the corresponding beta 2 is 0. If you take BK7 as an example, this is 1322 nanometers, as I showed you in last page. Either way, case 1 or case 2 happens, cubic phase is important. So we need to derive the formulas. This is the formula for beta she, okay, in terms of variable omega or in terms of variable lambda. Okay. I skip the intermediate steps. You can just follow the same strategy. And in fiber optics, say you purchase a piece of fiber, you can check the spec. Usually you can find two key parameters. One is big D. What is big D? GVD parameter related to beta 2 about the quadratic spectral phase modulation, right? The other one is dispersion slope, big S, which is the derivative of big D. Okay? And if you substitute the formula of big D, performing another derivative with respect to lambda, you got this. 所以很多时候 maybe 这个三阶的 phase 不那么重要，但是特别是这个时候，这个就无可回避，因为二阶已经是0，你最开始的 phase 就必须从三阶考虑起。所以像是 fiber 呢 ，maybe 在1300纳米左右，那三阶的 phase 就非常明显。这时候你要考虑的就是 big S dispersion slope， 而不是 dispersion. Actually, this issue evolves with some history of fiber optics development. We know zero dispersion is around 1300 nanometers for long. Because if you use silica as the fiber material, zero dispersion wavelength is there. People know that a long time ago. So a very natural idea is why not to use laser sources at 1300 nanometers, because that is zero dispersion wavelengths. So supposedly, if you use 1300 nanometers lasers and the fibers, you can transmit the signal for a very long distance without the requirement of recompression, right? Because no dispersion. So it's a very grand advantage, very attractive. Okay. However, people later found that it's not a good choice. If you're working at 1300 nanometers, you will have zero beta 2, but in that case, the cubic phase dominates, and it's more difficult to deal with cubic phase. So eventually, people switch to 1500 nanometers, 1550 nanometers. Although the dispersion is not zero, but the loss is minimal. Okay, and you will suffer basically quadratic phase modulation. You need compression, but it's not too difficult. Any question? Okay, last page of this section. The need of a dispersion compensator. First, a Moloch laser can produce a true pulse. Do you still remember the materials in lesson 4? When we talk about passive Moloch lasers, the output pulse could be chirped if your cavity has non-zero dispersion and cell phase modulation, chirp effect. Your output pulse could be chirped. So in that case, anyway, you need dispersion compensation, right? Secondly, even you can generate a transform limited pulse from your Moloch laser, okay? It will get chirped by passing through optical elements. For any optical system, you need optical elements. And when your pulse passes through them, you got chirped. So you still need a dispersion compensator to compress it back to transform limit. And in theory, the chirping can be done by using a proper material of adequate thickness, right? In this lesson, we analyzed the formulas of material dispersion. So maybe if you have some chirp pulse, if you know the chirp, you can find some suitable material with adequate thickness, both. You can do dispersion compensation. But this seems not a very good idea, right? It's a case-by-case solution. Sometimes you can never find suitable material for your spatial chirp. Okay, so that's the issue I mentioned here. It's difficult to achieve a specific complementary spectral phase function for perfect chirping if you want to use material dispersion. And another thing is material anomalous dispersion is accompanied with absorption, just like what we analyzed. So it's lossy in compensating upchirp pulses. You have upchirp pulse. If you want to compress it, you need anomalous dispersion. But if you try to access anomalous dispersion, it's risky. You will run into the absorption region. So although you might compress your pulse, but you will lose some power, which is undesirable. Okay. So it means we need some other architecture to build up dispersion compensator instead of using material dispersion. Okay, let's take a rest of 10 minutes.